Hello, my name is Shahrzad and I'm a PhD student at Northumbria University, and I'm very glad that we're able to share our results with you in this conference. Our work is about a flexible PVDF-based platform by combining Acoustofluidics and Electromagnetic Metamaterials. The outline of my talk is I will explain our aim, I will go over a brief introduction about metamaterial-based resonators and also surface acoustic wave actuators. I will share with you our previous designs together with the results that we had and why we have decided to move on a PVDF-based substrate. And I will end my talk by a conclusion. In order to improve the global health, it is essential to improve the point-of-care testing devices. One of these point-of-care testing devices is called a lab-on-a-chip device or a log device, and it usually consists of different parts, and each part has a certain task. A lab-on-a-chip device can be small in size and can handle a very small amount of liquids and is also capable of sensing. Since it has different parts that are able to perform different functionalities, it makes its fabrication a bit challenging. And that is one of the reasons we don't see many of these devices in the market. So our aim is to address that challenge by combining sensing capabilities of metamaterial-based resonators and also actuation capabilities of surface acoustic wave actuators, but using a single design. Our aim is also to achieve high precision sensing in microwave frequencies together with fluid manipulation in radio frequencies, and our ultimate goal is to move this platform to a flexible substrate for taking advantage of wearable applications. Metamaterial-based resonators are artificially engineered structures that have unique electromagnetic properties such as negative values of refractive index. They can be non-invasive and can be excited wirelessly. They can have high precision and can be highly sensitive. The basic building blocks of metamaterials are called split ring resonators, which are basically metallic rings that have split or splits on them and are fabricated on a dielectric substrate. They can have a broad range of applications from microwave frequencies to visible light, and we are able to achieve high quality factors, usually more than 1,000. In here, you can see a picture with different devices, different research areas that have been utilized in chemical sensing and also physical sensing. Now I would like to talk about the operation principle of a split ring resonator. When a split ring resonator is exposed to electromagnetic wave, it can have an electric resonance or a magnetic resonance. By placing a split ring resonator between two monopole antennas, we're exposing it to a magnetic field and also electric field. And since the electromagnetic wave is radiated omnidirectionally from the antennas, depending on the direction of electric or magnetic field, different scenarios can happen. We call a resonance a magnetic resonance when there is a circulating current path induced inside a ring. And a fundamental magnetic resonance can be modeled as an LC resonator, in which the formula is shown in this slide. So it has two elements of effective inductance and also effective capacitance. Therefore, by changing the size, we're able to change the frequency. Also, dielectric constants is affecting the capacitance. Therefore, by changing the environment and dielectric constants, we're able to change the capacitance and therefore changing the frequency. So that is one way of using it as a sensor. There are different scenarios that can cause a circulating current path. So one is when the magnetic field is perpendicular to the device, therefore a circulating current is induced inside the ring. The second scenario is the magnetic field is perpendicular to the device, and also the electric field is contributing to that circulating by polarizing the gap of the ring. And in the third scenario, it's only electric field, which is polarizing the gap and therefore generating a circulating current. SRRs can have different applications, and in our past experiences. We have used it for sensing different concentrations of heparin and also material characterization. On the left-hand side, you can see the split ring resonator used in heparin sensing, and the surface of that was functionalized, and then different concentration of heparin was exposed to the device on the gap, and then by increasing the concentration of heparin, we were able to increase the capacitance, and therefore the frequency was shifting towards lower frequencies. On the right-hand side, you can see an embroidered split ring resonator, which was fabricated using conductive threads on a fabric, and it was wrapped around an empty bottle and was placed between two monopole antennas. And using a network analyzer, we characterized this device by an empty bottle. And in the next step, we filled the bottle with different substances, such as DI water, methanol, ethanol, acetone, IPA, and we have compared that to the empty bottle. Since each substance has a different dielectric constant, therefore it introduces a different capacitance, and therefore a frequency would be different. So it's a way of sensing the materials inside the bottle. So these are the advantages of metamaterial that they can be highly sensitive. But the drawback of metamaterial-based resonators is that they're not capable of manipulating the droplets. So that is why it brings us to surface acoustic wave actuators. Surface acoustic wave actuators are actually interdigitated transducers that are fabricated on a piezoelectric substrate, and they're capable of manipulating the biological fluids, such as mixing them, separate them, pump them, or cause them to jet. In this picture, in the first row, you can see that a droplet is filled by polystyrene particles, and by applying power to the surface acoustic wave device, acoustic waves are generated inside the substrate, and then these waves are transferred to the droplet and agitates the particles inside. Therefore, a mixing pattern has been shown. By increasing the power, we were able to achieve jetting and also nebulization. And since surface acoustic wave actuators are based on thin film technology, they are compatible with metamaterial realization. So by combining these two technologies, we came up with different designs, and in this slide and also next slide, you will see a design that we have used both for microfluidic functions and also sensing functions. In this slide, I would like to show you our results with microfluidic functionalities. So the design is shown in this slide, and by applying power to IDT pads, we were able to generate streaming in the figure that is in the middle, and by further increasing the power, we were able to pump the droplet, which is shown on top right-hand side of the slide. And by further increasing the power, we were able to jet the droplet, which is the bottom right picture. Using the same device, we can also achieve sensing with two different approaches. So one is we use it for glucose sensing with different concentration. By increasing the concentration of the glucose, the capacitance was decreasing, and therefore the frequency shifted towards higher frequencies. The sensitivity that was measured in this experiment was 28 megahertz per milligram per milliliter. And we also use this as a sensing mechanism of the distance between the droplet and also the sensor. So we place the droplet in front of our sensor and measure the resonant frequency. And afterwards, we move the droplet to further displacement, and then again measure the frequency. And we saw that by doing so, we are able to decrease the capacitance and therefore shift the resonant frequency towards higher frequencies. In this experiment, we showed that this device is capable of both the sensing and also microfluidic functions using two different technologies in two different frequency ranges. So we decided to move this platform onto a flexible platform. And one of our options is a PVDF substrate. PVDF is a polymer which can have piezoelectric properties, and it has distinct chemical, mechanical, and electrical properties. The design that we have used is shown in this slide. There are two different fabrication processes that can be done to achieve this shape. One can be a standard lift-off and photolithography process, and the other is using a readily available PVD substrate that is coated with silver and use laser milling to generate this pattern. These patterns can also be modeled as an LC resonator, which is shown at the right-hand side of the slide. We perform simulation using CST, and we are able to show that depending on the direction of electric or magnetic field, we can see different behaviors from this device. So in the part A, you can see that the electric field is polarizing the gap and creates a circulating current path and a magnetic resonance. In B, the magnetic field is perpendicular to the device. Also, electric field is polarizing the gap. So we can see that magnetic frequency and also an additional frequency that is caused by the magnetic field. In the third, which is part C, you can see that the magnetic field is generating two different magnetic frequencies, and in part D, neither electric field is polarizing the gap nor magnetic field is perpendicular to the device. Therefore, we don't see any resonances within the intended range. We also characterize the device using a network analyzer. On the left-hand side, we characterize the device within microwave range frequencies, and we were able to measure a frequency around 3.5 gigahertz. On the right-hand side, you can see the characterization of the acoustic resonance, which was made in radio frequencies. And the device itself has a frequency of 3.2 megahertz. And when the device is placed on a lithium niobate substrate, which is also a piezoelectric substrate, we were able to show that the frequency would increase because the speed in the substrate would increase. We also characterize the device using a loop antenna, and you can see the frequency response of that device, which is shown in blue. And then afterwards, we introduce a droplet on top of the device, and we could see that by introducing a DI droplet on the device, we could shift the frequency towards lower frequency because the dielectric constants of water, the effective dielectric constant is 80, and for air it is 1. Therefore, by increasing the dielectric constant, we're increasing the capacitance, and therefore the resonant frequency will shift towards a lower frequency. So it is a way of showing that it can also be used as a sensor. So in conclusion, in this work, we introduced a design by combining surface acoustic waves and electromagnetic metamaterials on a single device, and the substrate used was a flexible PVDF substrate. The device exhibits an acoustic resonance at 3.2 megahertz and electromagnetic resonance at around 3.4 gigahertz. The acoustic resonance can be used for liquid manipulations. However, the magnetic resonance can be used for sensing functionalities. This method of fabrication is advantageous because it is scalable, it is low cost, and it can be applied to flexible substrates. We aim to continue our work by functionalization for specific detection and by optimizing our fabrication processes. So that was about my talk, and I would like to thank you for watching these slides and also listening to me. And we would be very happy to answer if you have any questions, either through this conference or through email. Thank you.